Hi, today we're going to be looking at a piece of kit which I picked up from eBay. So this is a Symmetricom GPS time and frequency receiver. So this is a GPS disciplined oscillator which I'm hoping to use as a frequency reference for the equipment in the lab. Now this was going with about 5 or 10 minutes spare on the auction, so I didn't really have much time to find out any specs on it, so I just placed a bid and hoped for the best, and no one else bidded on it, so I won it. But the problem is that this only has a 2.048 megahertz output. It still has the 1 pulse per second, and it's got some serial ports here, but I think this is geared more towards telecommunications use. So we may have to build some circuitry to get our 10 megahertz reference, or it may indeed just have a 10 megahertz oscillator inside and they've stepped it down to 2.048 megahertz. But literally I have no idea about this device. I had a quick cursory look on the internet to see if there were any data sheets or anything, but I think it's quite out of date now. So let's have a look inside and see what there is, and then we'll have to try hooking it up and see, you know, what the outputs do. So here's the unit itself. It's a 19-inch rack mount unit, and basically there's nothing on the front, there's no switches or anything. There's just 3 LEDs, so I think there's a red, yellow and a green LED, and it's just to give an indication of the status. So let's have a look at the back of the unit. Right, so on the rear we've got the GPS antenna input, so that's a TNC connector, and then we've got the 1 pulse per second and the 2.048 megahertz outputs on BNC connectors, and then there's two 9-pin D-sub connectors. This one says command channel and this one says time of day channel. I'm basically assuming that these are going to be RS-232 interfaces, but once we take the cover off we'll be able to see what's connected to those. And then we've got a 2 amp fuse, there's a green LED in a little recess here, and then there's a 4-pin connector and it just says 48 volts and 0.5 amps. There's also a earth binding post here, just if you needed to earth the chassis. But maybe one of these pins will also be connected to the chassis as well. Other than that, it just says, so it's made by Navstar Systems, and that says Northampton, England. So this was made in England. It's got a serial number or a part number of some kind. It just says GPS time and frequency receiver, and then 122778 is the number underneath the barcode. And I think that's about all there is. It's just a metal box, lots of screws. It's got quite a few screws on the top, nothing on the bottom, and then the front and the back just have all of these Torx screws as well on the holding everything together. So let's take the unit apart and see what's inside. And on the top here it looks like we've just got some posi drive screws, posi 1s. So we'll just find the correct bit for that, and we can start taking all the screws out. Okay, so let's lift the cover. It's a bit stiff. Aha! Okay, so we can immediately see we have what looks like a DC to DC converter. It has 5 volt output, 15 and minus 15 volts. We've got a little bit of filtering circuitry here just on the power input. We can have a look at that in a moment. There's the little board here for the 3 LEDs on the front, the GPS receivers here, and then it's all mounted on a motherboard with an Altera Max, I think that's a CPLD. There's an MC Motorola 68 processor here, and some flash and some RAM here, and possibly another processor just here. And then we've got a little polystyrene enclosure, so I assume that's the oven controlled oscillator, which it is. and that actually says 10 megahertz output, so we may just be able to tap off the 10 megahertz from here and maybe put another BNC on the back. It might be worth just buffering the output so that we don't interfere with anything else that it might be doing, but we'll take a look once we've got the board out. But let's have a closer look at the components that are on the board. So just starting with the input connector, we have our 4-pin connector for the 48 volt input. The little riser board that the connector's soldered to has a pair of capacitors on here, and then there's an 8-pin connector, a dual row header, which transitions this vertical board onto the main motherboard. Then we have the fuse holder and the little green LED, and a reverse polarity diode, a common mode choke, and some more inductors here, some additional capacitors, and then the bulk storage cap before we enter the DC to DC converter. And then just moving up to the DC to DC converter, they fitted an Artisan 25 watt DC to DC converter with plus 5 volt and plus or minus 15 volt outputs from the 48 volt input. The input voltage range is actually quite wide on this device. It's 36 to 72 volts. The total output power is 25 watts, but you can actually draw up to 5 amps from the 5 volt supply, or 0.8 amps from either of the 15 volt supplies, so long as the total dissipation of the entire device is less than 25 watts. But that was probably quite a schmick unit, quite expensive DC to DC converter, and it's specifically qualified for telecommunications type use. And then just moving up the board a little bit more, we have our output capacitors. They've got some tantalums here with a couple of jumpers. I don't know what the jumpers do. Maybe you can pull those off and put an ammeter on there. They look to be in series with possibly the output of the DC to DC. And you can also see the little riser board which has the front panel LEDs on. So let's look at the GPS board next. So here we have the GPS receiver board. This is also made by Navstar England, and presumably this is an existing design that they had at the time, and there wasn't any point in relaying that out on the board, so they've just attached it as a daughter board. But there's not actually many connections onto the main board. So we have our coax here, which is the GPS input, and we've got another coax going down onto the main board. But then the only other connection I can see onto the main board is this 8-pin 0.1 inch header just here. And there doesn't really seem to be any processing power on this board, and there probably wasn't anything available kind of at that time for doing that kind of thing. So probably all we have on here is the low noise amplifier, the down converter, and probably the intermediate frequency amplifier, and then it probably goes straight onto the main board with this coax here, although this does seem to be very close to the 1 pulse per second BNC connector, but I'm sure that's not just for the 1 pulse per second output. So just looking a bit closer at the components that are visible on the board, we've got a pair of Max 961 high-speed comparators here. We've got an LMC 6482 rail-to-rail op-amp. There's a BCP51 PMP transistor here, and a National Semiconductor 2951 voltage regulator here. So there's not really a lot going on the board that we can see. And I've just got my mirror here, and I can't actually see anything, else under the board. So there's not really a lot going on that going on the GPS board itself. So I assume the majority of the stuff's going on this CPLD and the processors that are on the board. So if we just move around the board a little bit more, at the top here we've got just a bit of logic and interfacing, and then just here we've got some Intel chips. These are PA28F200 2 megabit flash chips, and we've got a bank of 4 of those. And then if we just move down a little bit more, we've got some Gold Star GM76C256 32 kilobyte RAM, so we've got a bank of 4 of those as well. And then just beneath that what I thought might have been a microprocessor is actually an NXP SC26C92 dual UART chip with a 3.6864 megahertz crystal, and it looks like a slightly odd frequency, but that does divide quite nicely down to give us 9600 baud or 19.2 kilobaud, and all the usual standard UART baud rates. And then just to the left of that, we've got a 20.48 megahertz crystal, which looks like I can see the signals going into a that's some logic, and then straight into the Altera Max PLD. And this is an EEPROM based PLD with 2500 gates and 128 macro cells. And then just next to that is where the GPS board is, so let's take the cover off. Let's take the board off there and have a look what's underneath. So we should now just be able to lift off the GPS board. Yeah, so there's just that 8-pin header joining onto the board. There looks to be a regulator here and a bit of logic. And then just here we've got some TC160G70AF CMOS gate arrays. And both of these are the same part. They've got 28,000 gates in it. And these are joined up to the chip above it, which is our processor that's running the system. So this is a Motorola MC68 EC series processor. It's actually a 32-bit processor with a coprocessor interface, and at full speed this thing runs at 25 megahertz and can dissipate 1.5 watts, so it might get a bit warm during use. And then if we just move up slightly more, we've got an unpopulated area here. This looks like a footprint for a PLCC socket, so there may have been either an alternate part to this part here. There looks to be some common signals going through, but yeah, I don't know what other options this device came in. And then the chip at the top here is a math coprocessor. So you can see a lot of the tracers moving around. And this is actually got quite reasonable specs. It's a 80-bit floating point processor with 64-bit mantissa and 15-bit signed exponent and 1-bit sign, and it's got a 67-bit ALU and barrel shifter. So clearly the processor and the coprocessor and the PLD are doing all of the GPS decoding and timing. So I'll just put the GPS board back, and we'll have a look at the oscillator section next. So to the left of the math coprocessor, we've got this Analog Devices 9734 10-bit SPI DAC, which is actually quite a nice part, and they're using this to control the adjust pin of the oven controlled oscillator. So the way the whole system works is it gets a lock on from the GPS system, and we get a frequency output from that, and then they slowly tweak the adjust pin on the oven controlled oscillator so that the 10 megahertz here matches the 10 megahertz which they've down converted or converted from the GPS receiver, so that even if we lose GPS lock, the oven controlled oscillator happily runs at basically the correct frequency. And then just to the left of here we've got a couple of National LF353 dual op amps. And then just here we've got our 10 megahertz. It looks like a single oven oscillator. You can usually tell because it's a bit smaller than the double oven oscillators, but I just peeled back the polystyrene here, and you probably can just see that on camera. There is an alternate footprint that's a little bit bigger, so it may be that we could install a 10 megahertz double oven oscillator for a bit of extra stability. There seems to be a room around the outside, so that might be something we can look at when we get the board out and see how it works. So what I want to do now is just find out what the pins on the DC connector do. and I can immediately see that one of these is connected directly to the chassis, but what I want to find out is where we attach our 48 volts. So we've got a bulk capacitor here feeding the DC to DC, and we've got the negative marking on the left hand side here. So let's have a look and see if any of those pins connect directly here. Okay, so the bottom one here is our negative supply, and then if we look at the other side, so I'm not getting anything there, but we do have this series diode to prevent reverse polarity. So if I just poke the probe on the opposite side of the diode, so this top right here is our plus 48 volts. Yeah. Okay, so I'll probably just solder some wires onto those two pins for now, because this connector is going to go if it all works. I'm going to try and put a 48 volt power supply in the casework so it's all self-contained. So I'll just solder some wires on and then we'll have a go at powering up the device. Okay, so I've soldered a couple of wires on to the power connector, and we've got the Fluke 87 in series with the power supply. Power supply is set to 48 volts, so if I turn that on now, yeah, okay, so we're drawing 270 milliamps, and the status LED is just on red. So I haven't connected a GPS antenna or anything now, but that just seems to be steady red. Current seems fairly constant. I guess as the crystal warms up, we should start to see that fall. Right, so that dropped quite rapidly to 167 milliamps. I'd be surprised if the oven controlled oscillator had cooled down that quick. And actually now it's ramping back up. So that's quite interesting. The current bounced around slightly there. It seemed to bounce to the two extremes and then slowly home in on the current that it's settled on now at 190 milliamps. But what we'll do now is we'll hook up a GPS antenna, and maybe we'll hook up the one of the serial ports as well and see if they're doing anything. And I've got one of these cheap magnetic car type GPS antennas, and then a slightly bigger marine application type GPS antenna. For now I'm just going to hook up the receiver to this one that I can just stick out the window, but I'm going to mount this one outside and just run the cable into the room. So we're just looking at the GPS receiver here, and before I connected up the GPS antenna I thought I'd just check the voltage that the antenna connection is providing, because the GPS antennas have a low noise amplifier built in. So you provide your supply voltage to the antenna, and then the GPS receiver also taps off the signal from the same line. And it was reading 12 volts between the centre pin and ground, and all of the GPS antennas I have I think are 3.3 to 5 volts. So I started having a look at the circuitry here, and there's 12 volts on this pin at the left, on the left here, and 5 volts on the pin above. And the 12 volt only seems to feed this circuitry here, and then that circuitry just seems to feed a supply to the GPS antenna. So the antenna itself is fed through a pass transistor here, and the only thing between that transistor and the 12 volt supply is a 21.5 ohm resistor. And then the base of that transistor seems to be driven by one of the op amps in this dual op amp package. And it looks like potentially the other op amp in this package is just being used to see if any current's being drawn by the antenna. So presumably if there's no antenna connected, it's it's detecting that no current is being drawn, so it doesn't even bother trying to do any of the GPS decoding. I'm not sure whether to try and find a 12-volt GPS antenna or whether to start modifying this circuit. I'm half inclined just to remove this inductor here because there's a CLC network here feeding the 12 volts into the circuitry. I'm tempted just to lift this inductor and temporarily supply, just link out from here to here with a bit of wire so that we get 5 volts in there and see if it still works. So there is what appears to be a feedback pin just here, which is the one that's driven by the second op amp in this package. So the voltage level on that didn't seem to be very high. In fact, I think it was clamped at 0 volts with no GPS antenna. I think I might just try linking that out and see if we can get 5 volts on the output and whether it causes any problems. Okay, actually I decide I would possibly sacrifice one of the cheap GPS antennas I have. So I've got I think it's about a £4 GPS antenna off Amazon connected to the unit. So if I power it up now, so now the status LED is flashing red. So I presume that means it's now looking for satellites. So I'll just turn that off quickly before we burn out the GPS antenna. And at least now if I modify that supply voltage to that circuitry on the board, we'll know if it's behaving the same way after the modification. Okay, so just to maintain some kind of filtering, I have put an inductor on the board between the 5 volt supply and where we want to feed the 5 volts into. I've only got a large one. I'll have to order a smaller filter at some point, but this will do for now just to test the idea. So I've still got my cheap GPS antenna connected to the GPS port. So if I turn on the power supply now, so the status LED is still flashed as it should do, and the red LED is flashing like it was before, so it still seems to think that there's an antenna connected. And if I just kind of check the voltage on the antenna connector, it's reading 4.1 volts, which is fine. These antennas are 3 to 5 volts that I've got, so that's absolutely fine. So I'll just put this antenna out the window and we'll see, well, firstly if we get any information from any of these serial ports, because I don't know if these do anything, and we'll also have a look and see if there's any frequency output from either of the BNC connectors on the back. Right, so I've just connected the 2.048 MHz output of the GPS receiver to my counter. The counter's not calibrated or anything, so it won't be reading spot on, hence the reason why I want a 10 MHz reference in the lab. But it does seem to be reading basically spot on 2.048 MHz. So at the moment I'm assuming that's just coming from the oven controlled oscillator rather than having been synchronized by the GPS receivers, because that red light's still flashing. Hopefully that red light will stop flashing and we'll get a different color soon, but it may be trying to get a lock on the GPS satellites first, so we'll see what happens there. I don't think we'll get anything from the 1 pulse per second output, and I don't think the counter will pick that one up anyway, because the pulse width usually of these GPS receivers on the 1 pulse per second output is pretty narrow, and these quite like a reasonable duty cycle. So I will hook it up just to the scope to see if there's any signal coming from there, but I suspect we'll have to wait until we get GPS lock before we get anything on the 1 pulse per second output. Right, so I've just hooked up the 2.048 MHz output to the scope with a bit of 50 ohm termination here, just to see what the waveform looks like. And we seem to have a square wave output, the 0 to 3.3 volt output, and the scope's also reading 2.048 MHz, so that's fine. So if I connect up the 1 pulse per second instead, Now I suspect we won't receive anything on here until we get a GPS lock. Okay, yeah, so there's nothing on there yet. So we'll wait and see if this light does anything other than flash red. So we've got a flashing green LED now. I'm just hooking up a serial port to the back of the receiver just to see if we're getting anything on any of the ports at the back. Right, so I've just hooked up the two serial ports at the back of the unit to the PC, and I've opened two instances of PuTTY. I've assumed that the baud rate is 9600 baud, but at the moment it doesn't seem to be responding in any way. And I did quickly try a few other baud rates, but even if the baud rate was incorrect, we would see at least something, some activity on the USB to RS-232 converters. So it might be that until this green light stops flashing and becomes constant, it doesn't do anything, so we'll just see what happens. Oh, okay. So I don't know if you can see in the background there seems to be some data coming out of the serial port for the time of day channel, and actually it's reading the time now correctly. That seems to be... let me just have a look. Okay, so it's actually 15 seconds fast. But I think I read on the internet about leap seconds. So the time reported by the GPS is actually slightly fast compared to what we use as GMT. So that seems to make sense. It is spot on 15 seconds fast. So that seems about right. And it seems to be reading the date as well. So we've got 2015 and then 053, which I think is the day of the year. But the LED here is still flashing. I don't know if we're getting a 1 pulse per second output yet on the scope, so I'll have a look at that. And here's our 1 pulse per second output. So that's the 3 volt signal. Actually, that just changed pulse width, and the green LED is now constant on the front of the unit. It was reading 1 full division, but now it's just dropped to half of that. So the pulse width now is, where are we? Oh, I can't even see it. So 0.5 microseconds wide. It's inverted polarity, so every second we get a blip towards 0 volts, but 3 volts all the other times. So if we just pan back down to the unit, so we can see now the green LED on the front of the unit's on constant. So then just looking at the monitor here, we've got the year 2015, what appears to be the day of the year 053, and then the time 1939 and 11 seconds. And then we've got G and S, I don't know what that means. There's a 1, 2, 3, 4, 5, 7 character hexadecimal string just there, which seems to be incrementing 1 per second, so that might be second of the year or something like that, and then we've probably got a checksum at the end. But there's still nothing on the command channel screen, and if I press enter or type anything, we don't seem to get anything back. Yeah, so I'll have to dig around and see if I can find anything on the web about this unit, but for now it seems to be behaving how I want it to. So the time coming out the serial port is quite nice. I don't really need that, although I could use that for, you know, a really accurate clock in the room or something like that. But the frequency output seems to be working, and we're getting the 1 pulse per second output as well. So I guess in the next video we'll take the board out of the unit and have a look and see where we might be able to tap our 10 megahertz output from on the board. So anyway, thanks for watching. So now the neighbours officially think I'm nuts. I've just mounted the GPS antenna outside. I've used a standard TV antenna mast type arrangement and fixed that on the top of the pole, and the cable's now ran into the study where I am currently. So in the next video we'll hook that up, and we'll also have a look at the modifications that I'm going to make to the GPS unit. I did also think it might be quite nice to put a VFD on the front of the unit, which perhaps gives that time of day output, so we've got the clock on the front, but that's something we'll investigate next time as well. So thanks for watching.